something is wrong with reality. Not wrong in the way that you might forget where you placed your keys, or wrong like a clock that runs a few seconds slow. This is something far deeper, something woven into the very fabric of existence itself. Scientists at some of the most advanced research facilities on Earth have been quietly uncovering evidence that the rules we thought governed the universe may not be quite right. The equations that have served physicists so well for decades, the mathematics that predicted everything from the existence of exotic particles to the precise behavior of light itself, are beginning to show tiny fractures, hairline cracks in the foundation of what we understand to be real. And if you are watching this video, if you have made it this far, then you deserve to know the full story. So settle in, get comfortable. Let the gentle hum of discovery wash over you as we explore together one of the most profound mysteries in modern science. Because what researchers have found suggests that our universe might be hiding something extraordinary, something we never expected, something that could change everything we think we know about the cosmos and our place within it. If you find this journey as fascinating as we do, take a moment to hit that like button and subscribe to Cosmic Drift. We explore the deepest mysteries of the universe together, one quiet revelation at a time. Now, let us begin at a place where the impossible becomes possible, where particles dance at nearly the speed of light, where the secrets of creation itself are being slowly, carefully, patiently unveiled. The story starts beneath the rolling hills of the Swiss and French countryside, in a circular tunnel that stretches for 27 kilometers. This is the home of the Large Hadron Collider, often simply called the LHC, the most powerful particle accelerator ever constructed by human hands. Here, in this underground cathedral of science, beams of protons are accelerated to velocities so extreme that they travel at 99.9999% the speed of light. When these beams collide, they release energies that briefly recreate conditions not seen since the first fraction of a second after the Big Bang itself. The European Organization for Nuclear Research, known by its French acronym CERN, operates this magnificent machine. For decades, CERN has been at the forefront of humanity's quest to understand the fundamental nature of reality. Their discoveries have reshaped our understanding of the cosmos time and time again. In 1983, experiments at CERN confirmed the existence of the W and Z bosons, particles that carried the weak nuclear force, one of the four fundamental forces of nature. This discovery earned Carlo Rubbia and Simon van der Meer the Nobel Prize in Physics just 1 year later. But perhaps the most famous moment in CERN's history came on July 4th, 2012. On that summer day, scientists announced to the world that they had finally found what they had been searching for since the 1960s. The Higgs boson, sometimes poetically called the God particle, had at last been observed. This tiny, fleeting particle was the final piece of a puzzle that physicists had been assembling for half a century. Its discovery confirmed a theory proposed independently by Robert Brout, Francois Englert, and Peter Higgs, explaining how particles acquire mass through their interaction with an invisible field that pervades all of space. The standard model of particle physics, the theoretical framework that describes the fundamental building blocks of matter and the forces that govern them, was complete. Or so it seemed. You see, the standard model is one of the most successful scientific theories ever devised. It describes three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, with breathtaking precision. It predicts the existence of 17 fundamental particles, 12 matter particles called fermions, 4 force-carrying particles called gauge bosons, and the Higgs boson itself. The mathematics of the Standard Model have been tested in countless experiments, and time after time, the predictions match reality with extraordinary accuracy. But here is the thing about the Standard Model that keeps physicists awake at night. Despite all its successes, they know it cannot be complete. There are too many things it cannot explain, too many mysteries it leaves untouched, too many questions it cannot answer. The Standard Model says nothing about gravity. While it beautifully describes electromagnetism and the nuclear forces, the fourth fundamental force remains stubbornly outside its reach. Einstein's theory of general relativity describes gravity as the curvature of space and time caused by mass and energy. But no one has been able to successfully merge this picture with the quantum mechanical framework of the Standard Model. Somewhere, somehow, these two great pillars of modern physics must connect, but we have not yet found the bridge between them. Then there is the mystery of dark matter. Astronomical observations tell us that the visible matter we can see, the stars, the galaxies, the planets, the nebulae, makes up only about 5% of the total mass and energy in the universe. Another 27% consists of something called dark matter, a mysterious substance that interacts with gravity but does not emit, absorb, or reflect light. We know dark matter exists because we can see its gravitational effects on galaxies and clusters of galaxies. Without it, stars at the edges of spiral galaxies would fly off into the void, unable to complete their orbits. Yet the Standard Model has no particle that could account for dark matter. Whatever it is, it lies beyond the boundaries of our current understanding. And dark matter is not even the strangest part. The remaining 68% of the universe's mass energy content consists of something even more enigmatic called dark energy. This mysterious force is accelerating the expansion of the universe, pushing galaxies apart at ever-increasing speeds. The Standard Model offers no explanation for dark energy whatsoever. It is as if 95% of the universe exists in a realm that our best theories simply cannot touch. There is also the puzzle of antimatter. According to the Standard Model, matter and antimatter should have been created in equal amounts during the Big Bang. When a particle meets its antiparticle, they annihilate each other in a burst of pure energy. If equal amounts of matter and antimatter had been created, they should have completely destroyed each other, leaving behind a universe filled with nothing but radiation. No stars, no planets, no you, no me. Yet, here we are. Something caused a slight imbalance, a tiny preference for matter over antimatter, allowing a residual amount of matter to survive and form everything we see today. The Standard Model cannot explain why this asymmetry exists. These are not minor loose ends. These are fundamental gaps in our understanding of reality. And it is precisely because physicists know the Standard Model must be incomplete that they scrutinize every measurement, every experiment, every tiny deviation from predicted behavior, because somewhere in those deviations might hide the first glimpses of physics beyond the Standard Model. Somewhere in the cracks, new truths might be waiting to be discovered. And this brings us to the crack that has captured the attention of the physics world, a discrepancy so subtle that measuring it required decades of effort and some of the most precise experiments ever conducted. Artiat wobble in the spin of a particle that should not exist, at least not according to the mathematics of the Standard Model. The particle at the center of this mystery is called the muon. If you have never heard of muons before, you are not alone. They are not household names like electrons or protons, but muons play a crucial role in particle physics, and they may hold the key to unlocking secrets that have remained hidden for generations. Muons are essentially heavier versions of electrons. Like electrons, they carry a negative electric charge. Like electrons, they are classified as leptons, a family of particles that do not experience the strong nuclear force. But while electrons are stable and can exist indefinitely, muons are fleeting visitors to our reality. A muon that pops into existence, perhaps created when a cosmic ray strikes the upper atmosphere, will survive for only about 2.2 microseconds before decaying into an electron and 2 neutrinos. 2.2 microseconds might seem impossibly brief, but in the world of particle physics, it is actually quite long. Many exotic particles live for trillionths of a second before vanishing. The muon's relative longevity makes it an ideal subject for precision experiments. Scientists have enough time to study muons, to manipulate them, to watch how they behave in magnetic fields, to measure their properties with exquisite care. The property that has drawn so much attention is called the magnetic moment. Every charged particle that spins acts like a tiny magnet, generating its own magnetic field. The strength of this miniature magnet is characterized by a number called G, the gyromagnetic ratio. According to the original quantum mechanical theory developed by Paul Dirac in the late 1920s, the G factor for electrons and muons should be exactly 2. This was an elegant prediction arising naturally from the mathematics of quantum mechanics and special relativity. But nature, as it often does, turned out to be more subtle than the initial theory suggested. As physicists developed more sophisticated theories in the 1940s and 50s, they realized that G should not be exactly 2. Quantum field theory predicts that empty space is not really empty at all. It seethes with fleeting, ghostly particles that pop into and out of existence so quickly that they cannot be directly observed. These virtual particles form a kind of quantum foam, constantly bubbling just beneath the surface of reality. When a muon moves through this quantum foam, it interacts with these virtual particles. The interactions are impossibly brief, lasting for tiny fractions of a second, but they have real measurable effects. They cause the muon's magnetic moment to be slightly larger than the naive prediction of 2. The difference between the measured G factor and the value 2 is called the anomalous magnetic moment, and it is typically written as G minus 2, or sometimes as the Greek letter A, with a subscript denoting the muon. The Standard Model allows physicists to calculate this anomalous magnetic moment with incredible precision. The calculation takes into account all the known particles and forces. Virtual photons contribute to the anomaly. So do virtual electrons and positrons. Virtual quarks and gluons add their effects through a contribution called the hadronic vacuum polarization. Even the W and Z bosons and the Higgs boson itself leave their tiny fingerprints on the muon's wobble. When you add up all these contributions, you get a prediction for the muon's anomalous magnetic moment that extends to many decimal places. This is one of the most precisely calculated quantities in all of physics, and for decades, the measurements agreed with the calculations. The Standard Model worked. Everything fit, until it did not. The first hints of trouble emerged at Brookhaven National Laboratory in New York in the late 1990s and early 2000s. A collaboration of physicists had constructed an experiment specifically designed to measure the muon's anomalous magnetic moment with unprecedented precision. They built a massive storage ring, a circular tube surrounded by powerful magnets, where muons could be trapped and studied as they circled around and around. As the muons traveled through the magnetic field, their spins precessed, which is a fancy way of saying that the direction of their tiny internal magnets slowly rotated, like a wobbling top. By measuring this precession rate extremely carefully and comparing it to the strength of the magnetic field, the scientists could determine the value of G-2. The result they obtained was intriguing. The measured value was slightly higher than what the standard model predicted, not by much. The difference was tiny, far smaller than the quantities being measured, but it was there, stubbornly persistent, refusing to go away even as the experimenters improved their techniques and gathered more data. Still, the discrepancy was not large enough to claim a definitive discovery. In particle physics, scientists use a statistical measure called sigma to quantify how confident they are that a result is real rather than a statistical fluke. A deviation of 3 sigma means there is about a 1 in 740 chance that the result is just random noise. 5 sigma, the gold standard for a discovery in particle physics, corresponds to roughly a 1 in 3.5 million chance. The Brookhaven result reached about 3.7 sigma, tantalizing but not conclusive. To resolve the mystery, a new experiment was needed, one that could push the precision even further, that could gather more data, that could control systematic errors with even greater care. And so, the muon G-2 experiment was born at Fermilab, the Fermi National Accelerator Laboratory in Illinois. In a remarkable feat of engineering, the 50-foot diameter storage ring from Brookhaven was carefully disassembled, shipped by barge around the eastern seaboard, up the Mississippi River, and then trucked across the Illinois countryside to its new home at Fermilab. There, surrounded by upgraded detectors and fed by a more powerful muon beam, the experiment began its quest to measure the muon's anomaly with the highest precision ever achieved. The results came in stages. In 2021, the collaboration announced their first measurements based on the initial year of data. The precision matched what had been achieved at Brookhaven, and crucially, the central value agreed with the earlier result. The discrepancy with the standard model persisted. Combined with the Brookhaven data, the new measurement reached a significance of 4.2 sigma. In 2023, more data were added, further improving the precision. And then, in June of 2025, the collaboration released their final result, incorporating all 6 years of data collection. The measurement had achieved a precision of 127 parts per billion, exceeding the original design goal of 140 parts per billion. This was the most accurate measurement of the muon's anomalous magnetic moment ever made, and it would likely remain the world's best for years to come. The experimental world average, combining all the data from Brookhaven and Fermilab, showed a clear, persistent deviation from certain theoretical predictions. Depending on which theoretical calculation you compared it to, the significance of the discrepancy ranged from around 3 sigma to over 5 sigma. And this is where things get complicated, because while the experimental picture has become crystal clear, the theoretical situation has grown murkier. You see, calculating the standard model prediction for the muon's anomalous magnetic moment is extraordinarily difficult. Most of the contributions can be computed with high precision using well-established techniques. But one piece of the calculation, called the hadronic vacuum polarization, poses enormous challenges. The hadronic vacuum polarization accounts for virtual quarks and gluons that briefly appear in the quantum foam surrounding the muon. Unlike electrons and photons, which interact through the relatively well-behaved electromagnetic force, quarks and gluons are governed by the strong nuclear force, described by a theory called quantum chromodynamics, or QCD. At low energies, QCD becomes notoriously difficult to calculate because the strong force is, well, strong. The usual mathematical approximation techniques that work so well for electromagnetism break down when applied to the strong force. For decades, physicists tackled this problem using what is called the data-driven approach. Instead of trying to calculate the hadronic vacuum polarization directly from first principles, they used experimental measurements of electron-positron collisions that produce hadrons. By measuring how often these collisions produce various combinations of quarks and antiquarks, and then using some clever mathematical relations, they could infer the contribution to the muon anomaly. This data-driven approach produced a standard model prediction that clearly disagreed with the measured value. The discrepancy stood at about 4 to 5 sigma, depending on the precise data and techniques used. It seemed like the muon was telling us that something was missing from the standard model, that some new particle or force was lurking just beyond the reach of current experiments. But then came the lattice. Lattice QCD is a computational technique that attempts to calculate the properties of the strong force from first principles by modeling space and time as a discrete grid, a lattice of points. Supercomputers simulate the behavior of quarks and gluons on this lattice, allowing physicists to extract predictions without relying on experimental data. In 2021, a collaboration called BMW published a lattice QCD calculation of the hadronic vacuum polarization that disagreed with the data-driven results. Their calculation suggested that the true standard model prediction might be higher than previously thought, closer to the experimental measurement. If correct, this would dramatically reduce the significance of the discrepancy. The tantalizing hint of new physics might evaporate into nothing more than a mirage caused by incomplete calculations. The theoretical community is now deeply engaged in trying to understand this disagreement. Are the data-driven methods missing something? Are the lattice calculations plagued by subtle errors? Or are both approaches correct within their stated uncertainties, pointing to some unknown systematic effect? The muon G-2 Theory Initiative, an international consortium of theorists, has been working to resolve these issues. They have published updated white papers incorporating new data and new calculations. As of mid-2025, tensions remain. Different approaches yield different predictions, and the true standard model value of the muon anomaly is still being debated. What does this mean for the crack in reality that we started with? It means that we are standing at a crossroads. The experimental measurement is rock solid. The muon behaves in a way that is now known with extraordinary precision. But whether that behavior deviates from the standard model depends on theoretical calculations that are still being refined. If the data-driven approach is correct, then the muon is screaming at us that something is missing from the standard model. Some new particle, some new force, some fifth fundamental interaction of nature is subtly influencing the muon spin as it wobbles through the magnetic field. If the lattice calculations are correct, then the standard model may yet survive this test. The crack may close, the anomaly may fade, and physicists will need to look elsewhere for hints of new physics. But here is the beautiful thing about science. This uncertainty is not a failure. It is the process working exactly as it should. Measurements push the boundaries of what we know. Theories struggle to keep up, Disagreements and debates sharpen our understanding, and eventually, slowly, the truth emerges. The muon anomaly has not revealed a definitive crack in the standard model, but it has exposed cracks in our calculations, cracks in our assumptions, cracks in our certainty. And it is precisely by probing these cracks that we will eventually break through to deeper truths. So let us continue our journey, because the muon is not the only particle that has been behaving unexpectedly. There are other anomalies, other discrepancies, other hints that reality may not be exactly what we thought. Consider the W boson. The W boson is one of the force carriers of the weak nuclear force, the interaction responsible for certain types of radioactive decay. Along with its neutral partner, the Z boson, the W was discovered at CERN in 1983. These particles are extraordinarily heavy by the standards of the subatomic world, about 80 times the mass of a proton. Their large masses explain why the weak force has such a short range, operating only over distances smaller than the diameter of a proton. The standard model makes a precise prediction for the mass of the W boson. Unlike some parameters that must be measured experimentally, the W mass can be calculated from other known quantities, the mass of the Z boson, the electromagnetic coupling constant, and the weak mixing angle. Once these are measured, the W mass follows from the mathematics of the theory. Any deviation between the predicted and measured W mass would be a smoking gun for physics beyond the standard model. For decades, measurements of the W boson mass agreed with predictions. Experiments at the Large Electron-Positron Collider at CERN, the Tevatron at Fermilab, and the Large Hadron Collider all produced consistent results, hovering close to the standard model expectation of about 80,357 megaelectron volts. Then, in April of 2022, the CDF collaboration at Fermilab dropped a bombshell. CDF stands for the Collider Detector at Fermilab, one of two major experiments at the now decommissioned Tevatron, a proton-antiproton collider that operated from 1983 to 2011. Even though the Tevatron had been shut down for over a decade, the CDF collaboration had continued analyzing their vast trove of data, refining their techniques, reducing their systematic uncertainties, pushing for the most precise measurement possible. Their result was stunning. They measured the W boson mass to be 80,433.5 megaelectron volts, with an uncertainty of only 9.4 megaelectron volts. This was the most precise measurement of the W boson mass ever made, and it disagreed with the standard model prediction by a whopping 7 standard deviations. 7 sigma is far beyond the threshold for discovery. If correct, the CDF result would represent a spectacular crack in the standard model, clear evidence that our fundamental theory of particle physics is incomplete. The physics community reacted with a mixture of excitement and skepticism. 7 sigma is an enormous discrepancy, too large to be explained by known statistical or systematic uncertainties. Either something revolutionary was happening, or something had gone wrong with the measurement. Other experiments began to weigh in. The Atlas collaboration at the LHC reanalyzed their data using improved techniques and found a W mass of about 80,366 megaelectron volts, much closer to the standard model prediction and in tension with the CDF result. The LHCb collaboration reported a measurement that also favored the standard model. Then, in September of 2024, the CMS collaboration at the LHC released their own measurement after 8 years of painstaking analysis. Their result, 80,360.2 mega-electron volts, with an uncertainty of just 9.9 mega-electron volts, was in beautiful agreement with the Standard Model and directly contradicted the CDF anomaly. The W boson mass mystery had taken a dramatic turn. 3 experiments at the LHC all found masses consistent with the Standard Model, while the CDF result remained an outlier. What was going on? The CDF collaboration stands by their result. They have conducted extensive cross-checks, scrutinized their detector calibration, examined possible sources of systematic error. So far, they have found no mistake. But the weight of evidence from the LHC experiments makes it increasingly likely that something unusual happened in the CDF analysis, some subtle effect that has not yet been identified. For now, the W boson mass anomaly seems to be fading. The cracks that appeared in 2022 are healing, at least partially. The Standard Model has survived another test. But this episode illustrates an important point about how science works at the frontier of knowledge. When you push measurements to extreme precision, strange things can happen. Systematic effects that were negligible at lower precision can suddenly become important. Theoretical assumptions that seemed reasonable can turn out to be wrong. The boundary between a revolutionary discovery and a subtle mistake can be razor thin. And yet, it is precisely by pushing to these extremes that we make progress. The CDF result forced experimenters around the world to sharpen their techniques, to scrutinize their methods, to test their assumptions. Even if the anomaly turns out to be an artifact rather than new physics, the process of investigating it will have advanced our understanding. So where does this leave us in our search for cracks in reality? The muon anomaly remains tantalizing but unresolved, dependent on theoretical calculations that are still being debated. The W boson mass anomaly appears to be receding, overwhelmed by consistent measurements from the LHC. But there are other hints, other whispers of physics beyond the Standard Model, other potential cracks waiting to be explored. One of the most intriguing possibilities is the existence of a fifth fundamental force of nature. Throughout history, physicists have gradually unified disparate phenomena under fewer and fewer fundamental forces. In the 19th century, James Clerk Maxwell showed that electricity and magnetism, which had seemed like separate forces, were actually two aspects of a single electromagnetic force. In the 1960s and 70s, physicists demonstrated that the electromagnetic force and the weak nuclear force could be unified into a single electroweak interaction at high energies. Today, theorists dream of a grand unified theory that would combine the electroweak force with the strong nuclear force, and ultimately a theory of everything that would incorporate gravity as well. But what if, instead of unifying forces, there is actually another force we have not yet discovered? What if the universe contains a fifth fundamental interaction, distinct from gravity, electromagnetism, and the nuclear forces, that has somehow escaped detection? This idea is not as outlandish as it might sound. The Standard Model of particle physics has gaps and inconsistencies that a fifth force could potentially explain. The existence of dark matter suggests that there may be particles that interact through forces we have not yet identified. The accelerating expansion of the universe hints at some kind of dark energy that might be related to new physical interactions. Over the years, physicists have searched for signs of a fifth force in many different contexts. They have looked for tiny deviations from Newton's law of gravity at short distances. They have examined atomic transitions for unexplained energy shifts. They have studied the orbits of celestial bodies for anomalies that known physics cannot explain. So far, no definitive evidence for a fifth force has been found. But the searches continue, and recent results have added new twists to the story. In 2024, a team of researchers used data from the OSIRIS-REx mission, which visited the asteroid Bennu, to search for evidence of a fifth force. The idea was clever. If some new force existed, mediated by hypothetical particles called ultralight bosons, it might cause subtle deviations in Bennu's orbit as the asteroid moved through the solar system. By comparing the predicted orbit based on known physics to the actual observed trajectory, scientists could place limits on the strength of any such fifth force. The researchers did not find evidence for a fifth force, but they were able to rule out certain theoretical models, narrowing the range of possibilities. And they demonstrated a new method for probing fundamental physics using asteroid tracking data, opening up a whole new avenue for future research. Meanwhile, other physicists have been searching for signs of a fifth force inside atoms. In 2025, researchers from Germany, Switzerland, and Australia reported intriguing results from measurements of atomic transitions in different isotopes of calcium. They were looking for discrepancies between measured transition frequencies and theoretical predictions, discrepancies that might signal the existence of a Yukawa-type interaction, mediated by a new particle. Their results were not conclusive. The uncertainties in both the measurements and the theoretical calculations were too large to make a definitive statement, but they were able to place new constraints on where such a fifth force might be hiding, narrowing the parameter space that future experiments will need to explore. The search for a fifth force is one of the most exciting frontiers in fundamental physics. If such a force exists, it could revolutionize our understanding of the universe. It might explain dark matter. It might reveal new particles with exotic properties. It might point the way toward a deeper theory that unifies all the forces of nature. But finding a fifth force, if it exists, will not be easy. Any new force must be extremely weak, or it would have been detected long ago. It must operate in a regime that current experiments can barely access. It must leave only the faintest of fingerprints on the phenomena we can observe. This is why the muon anomaly is so exciting. If new physics exists, it might first reveal itself through tiny, subtle effects that only the most precise experiments can detect. The muon, with its convenient lifetime and its sensitivity to virtual particles, is an ideal probe for such effects. A confirmed discrepancy between the measured and predicted values of the muon's anomalous magnetic moment could be the first solid evidence that a fifth force, or some other form of new physics, truly exists. But we are not there yet. The theoretical disagreements must be resolved. The calculations must be refined. More data must be gathered and analyzed. The process of science must continue. And so, let us continue our journey deeper into the mysteries of the cosmos. Because the potential cracks in the standard model are not limited to particle physics, they extend outward to the very structure of the universe itself. When astronomers look out at the cosmos, they see a universe that is expanding. Galaxies are moving away from each other, carried along by the stretching of space itself. This expansion was first discovered by Edwin Hubble in the 1920s, when he noticed that distant galaxies had their light shifted toward the red end of the spectrum, a sign that they were receding from us. The rate of this expansion is characterized by a number called the Hubble constant. In principle, the Hubble constant should be a straightforward quantity to measure. You look at distant galaxies, you determine how fast they are moving away from us. You figure out how far away they are, and you calculate the ratio. Simple, right? Not quite. It turns out that measuring the Hubble constant with precision is extraordinarily difficult. There are many different methods using many different types of astronomical objects, and they do not all agree. One approach uses observations of the cosmic microwave background, the faint glow of radiation left over from the hot, dense early universe. By analyzing tiny fluctuations in this radiation, cosmologists can infer the properties of the universe shortly after the Big Bang and extrapolate forward to determine the current expansion rate. This method, based on data from satellites, like the Planck mission, gives a Hubble constant of about 67 kilometers per second per megaparsec. Another approach uses observations of nearby supernovae, exploding stars whose intrinsic brightness is well known. By comparing this intrinsic brightness to how bright they appear from Earth, astronomers can determine their distances. Combined with measurements of how fast their host galaxies are receding, this yields the Hubble constant. Teams using this method have consistently found a higher value, around 73 kilometers per second per megaparsec. The discrepancy between these two approaches is called the Hubble tension, and it has persisted stubbornly for years despite increasingly precise measurements. The difference is small in absolute terms, only about 9%, but both methods claim uncertainties of only a few percent, so the disagreement is statistically significant, reaching beyond 5 sigma in some analyses. What does this mean? One possibility is that one or both measurement methods has a systematic error that has not been properly accounted for. Perhaps the cosmic microwave background analysis relies on assumptions about the early universe that are not quite correct. Perhaps the supernova measurements are affected by dust or other astrophysical effects that have been underestimated. But another, more exciting possibility is that the Hubble tension is a sign of new physics. If the universe behaved differently in its early history than our current models assume, it could explain why measurements based on the early universe give a different answer than measurements based on the late universe. What kind of new physics might be involved? There are many proposals. Perhaps dark energy is not constant, but evolves over time, changing the expansion history of the universe. Perhaps there were extra relativistic particles in the early universe, more than the standard model predicts, affecting how the cosmos evolved. Perhaps dark matter interacts through forces we have not yet discovered, altering the growth of cosmic structures. The Hubble tension, like the muon anomaly, is a crack that might lead nowhere, or might lead everywhere. It could be resolved by better measurements and more careful analysis. Or it could be the first glimpse of physics beyond our current understanding, and there are more cracks, more tensions, more anomalies scattered throughout physics and cosmology. The growth of cosmic structure seems to be slower than some models predict, a discrepancy called the sigma-8 tension. Measurements of the curvature of the universe give slightly different answers depending on which data sets are used. The masses of neutrinos, the ghostly particles that barely interact with ordinary matter, remain mysterious, and hints from different experiments sometimes point in different directions. Each of these anomalies could be a statistical fluctuation, an experimental error, a theoretical miscalculation. But each could also be a window into new physics, a crack in our understanding that leads to something deeper. The history of physics is filled with examples of small anomalies that led to revolutionary discoveries. The precession of Mercury's orbit, a tiny discrepancy from Newtonian predictions, pointed the way to Einstein's general relativity. The ultraviolet catastrophe, a failure of classical physics to predict the spectrum of thermal radiation, gave birth to quantum mechanics. The unexpected stability of the atomic nucleus demanded a new understanding of the forces holding matter together. The anomalies we see today may be the precursors of tomorrow's revolutions, or they may fade away as our measurements and calculations improve. We cannot know in advance which path history will take, but we can continue to search. We can continue to measure. We can continue to push the boundaries of precision, probing ever deeper into the fabric of reality. And that is exactly what thousands of physicists around the world are doing right now, as you listen to these words, as you drift towards sleep, as the mysteries of the cosmos swirl gently through your mind. The Large Hadron Collider is not standing still. It continues to operate, smashing protons together, generating vast amounts of data, searching for any signs of particles or phenomena that lie beyond the standard model. A major upgrade, called the High Luminosity LHC, is scheduled to begin operations in 2030. This enhanced machine will produce far more collisions than the current accelerator, greatly increasing the chances of spotting rare processes that might reveal new physics. Beyond the LHC, even more ambitious machines are being planned. CERN is studying the possibility of building a future circular collider, a 90-kilometer ring that would dwarf the current accelerator and probe energies far beyond what is currently accessible. Other proposals include electron-positron colliders that could study the Higgs boson and other particles with unprecedented precision. At Fermilab, even though the muon G-2 experiment has concluded its data taking, the analysis will continue for years, and a future experiment at the Japan Proton Accelerator Research Complex will make independent measurements of the muon anomaly using a completely different technique, providing a crucial cross-check of the results. Astronomers are deploying new telescopes and surveys that will map the universe in exquisite detail, testing cosmological models and searching for hints of physics beyond the standard picture. The Dark Energy Spectroscopic Instrument, or DESI, is measuring the positions and distances of tens of millions of galaxies, looking for subtle signatures of how dark energy has shaped the expansion of the cosmos. The Vera C. Rubin Observatory will soon begin its decade-long survey of the southern sky, detecting supernovae, asteroids, and countless other transient phenomena that will illuminate the workings of the universe. Theoretical physicists are developing new frameworks, new models, new mathematical tools to understand what lies beyond the standard model. Supersymmetry, extra dimensions, string theory, loop quantum gravity, emergent spacetime. Each of these ideas offers a different vision of what the deeper theory might look like. Most of these ideas will probably turn out to be wrong, but one of them, or perhaps something not yet imagined, might capture the truth. This is the grand adventure of physics, the endless quest to understand reality at its most fundamental level. It is a quest that stretches back to the ancient Greeks who first asked what the world is made of, through Galileo and Newton, and Maxwell and Einstein, and Bohr and Feynman, down to the researchers working today in laboratories and observatories and universities around the globe. And you are part of this adventure too. By watching this video, by learning about the mysteries of the cosmos, by wondering about the nature of reality, you are participating in one of humanity's noblest endeavors. You are joining a conversation that spans millennia and circles the entire world. So let us return once more to the question we started with. Is there really a crack in reality? The honest answer is that we do not know yet. The muon anomaly is intriguing but not definitive. The theoretical uncertainties cloud the interpretation. The W boson mass anomaly that seemed so dramatic in 2022 has largely faded in the face of new measurements. The Hubble tension persists, but its resolution might come from better astrophysics rather than new physics. And yet, the standard model is incomplete. We know this for certain. It does not explain dark matter. It does not explain dark energy. It does not incorporate gravity. It does not explain why matter dominates over antimatter. It has too many free parameters, too many unexplained patterns, too many questions left unanswered. Somewhere, there must be physics beyond the standard model. Somewhere, reality must be richer and stranger than our current theories suggest. The cracks may be subtle, nearly invisible, hidden in the 15th decimal place of some obscure measurement. But they are there waiting to be found. The story of physics in the coming decades will be the story of finding those cracks and prying them open. It will be the story of new experiments, new theories, new discoveries that reshape our understanding of the cosmos. It will be a story filled with false starts and dead ends, but also with genuine breakthroughs that illuminate the deepest mysteries of existence. What role will the muon play in that story? Only time will tell. Perhaps the theoretical disagreements will be resolved, and the muon anomaly will turn out to be consistent with the standard model after all. Or perhaps the calculations will converge on a value that clearly differs from experiment, pointing unmistakably toward new physics. Either outcome will advance our understanding. Either outcome will be a victory for science. Because the goal is not to prove the standard model wrong. The goal is to understand reality. If the standard model survives every test we throw at it, that tells us something profound about the laws of nature. If it fails, that tells us something even more profound. In science, there are no losers, only learners, and so we wait, and we watch, and we wonder. We dream about what the universe might be hiding just beyond the reach of our current knowledge. We imagine particles we have never seen, forces we have never felt, dimensions we have never explored. The universe is vast and ancient and strange beyond measure. We are tiny, creatures on a small planet, orbiting an ordinary star in an unremarkable galaxy, one among hundreds of billions of galaxies in the observable universe. And yet, against all odds, we have managed to understand so much. We have mapped the particles and forces that make up matter. We have traced the history of the cosmos back to the first fractions of a second. We have sent machines to other worlds and built detectors that can sense the vibrations of space-time itself. What we have accomplished is astonishing. What remains to be discovered is beyond imagination. Let these thoughts carry you gently into the night. Let the mysteries of the muon and the W boson and the Hubble tension drift through your consciousness like stars wheeling slowly overhead. Let the wonder of it all fill you with a quiet peace, because we are all part of this great adventure. We are all made of particles that emerged from the Big Bang, atoms forged in the hearts of ancient stars, stardust and quantum foam, and cosmic microwave background radiation. We are the universe contemplating itself, matter that has somehow become aware, particles that have learned to ask questions about particles, and the questions we ask matter, the search for cracks in reality, for physics beyond the standard model, for deeper truths about the nature of existence. This is not just an abstract intellectual exercise. It is part of what makes us human. It is the same drive that led our ancestors to look up at the night sky and wonder what the lights in the darkness might be. The Large Hadron Collider is quiet now, at least for this brief moment. The muon storage ring at Fermilab has completed its final runs. The detectors and the magnets and the computer systems are all waiting for the next round of experiments, the next round of measurements, the next round of discoveries. And somewhere, in some laboratory or observatory or theorist's office, someone is having an idea that will change everything. Someone is looking at data that no one has looked at quite the same way before. Someone is asking a question that leads, eventually, inexorably, to a revolution in our understanding. That is the beauty of science. The story is never finished. There is always more to learn, more to explore, more to discover. The cracks in reality, whatever they turn out to be, are doorways to knowledge we cannot yet imagine. So rest now. Let your mind wander through the mysteries we have explored together. Think of muons wobbling in magnetic fields, of W bosons carrying the weak force, of photons from the cosmic microwave background carrying information across billions of years. Think of the dedicated scientists who spend their careers chasing tiny anomalies, hoping to catch a glimpse of something new. And know that the universe, in all its vastness and complexity and beauty, is waiting to share its secrets with anyone patient and curious enough to listen. The cracks in reality may be small, but the truths they reveal could be infinite. Sleep well, fellow traveler among the stars. The journey continues tomorrow. There is something deeply comforting about the way the universe reveals its secrets. It does not rush. It does not shout. It whispers gently, persistently, to those who are patient enough to listen. And tonight, as you settle deeper into whatever soft place you have found, let us continue listening together. We have spoken of the muon, that heavy cousin of the electron, and how its strange wobble might be telling us something profound about the fabric of reality. We have explored the W boson, the carrier of the weak force, and the brief excitement when one measurement seemed to contradict everything we thought we knew. We have touched upon the Hubble tension, the disagreement between different ways of measuring how fast the universe is expanding. But there is so much more to this story. The quest to understand reality at its most fundamental level is not just about finding anomalies and hoping they point to new physics. It is about building a coherent picture of the cosmos, one piece at a time, one experiment at a time, one breakthrough at a time. Let us go deeper. To truly appreciate what is at stake when physicists talk about cracks in the Standard Model, we need to understand what the Standard Model actually is and how it came to be. Because the Standard Model is not just a list of particles. It is a towering intellectual achievement, the culmination of centuries of scientific inquiry, the most precise description of nature ever devised by the human mind. The story begins, in a sense, with the ancient Greeks. Philosophers like Democritus proposed that all matter was made of tiny, indivisible particles called atoms. This was pure speculation, of course. They had no way to test their ideas, no experiments to perform, no microscopes to peer into the heart of matter. But the intuition was there, the sense that beneath the bewildering variety of the natural world, there must be some simple, underlying structure. 2,000 years passed before this intuition could be put to the test. In the 19th century, chemists like John Dalton showed that chemical reactions could be explained by assuming that matter was made of atoms of different elements, each with its own characteristic mass and properties. By the end of the century, the periodic table had been established, organizing the elements into a pattern that hinted at some deeper order. But atoms, it turned out, were not truly indivisible. In 1897, J. Thomson discovered the electron, a tiny negatively charged particle that could be stripped from atoms. This meant that atoms had internal structure. they were not the ultimate building blocks of matter after all. The discovery of the electron opened a new era of exploration. Over the next few decades, physicists discovered that atoms consisted of a small, dense, positively charged nucleus surrounded by a cloud of electrons. The nucleus itself was made of protons and neutrons, particles about 2,000 times heavier than electrons. And as accelerator technology improved, physicists began smashing particles together at higher and higher energies, revealing an ever-growing menagerie of new particles. By the 1950s and 60s, the situation had become bewildering. There were electrons and protons and neutrons, yes, but also muons and pions and kaons and sigmas and lambdas and deltas and countless others. It was like the periodic table of chemistry all over again, except even more chaotic. Physicists spoke of a particle zoo, and they desperately sought some organizing principle that could make sense of the proliferating list. The breakthrough came from Murray Gell-Mann, and independently, George Zweig. They proposed that most of the newly discovered particles were not fundamental at all. Instead, they were made of smaller constituents called quarks. In the original model, there were 3 types of quarks, whimsically named up, down, and strange. Protons and neutrons were composed of 3 quarks each. Pions and kaons were made of a quark and an antiquark. The bizarre zoo of particles suddenly made sense as different combinations of a few fundamental building blocks. The quark model was a triumph, but it raised new questions. If quarks were real, why had no one ever seen an isolated quark? Why did quarks seem to be permanently confined inside protons and neutrons? What force held them together? The answer came from a theory called quantum chromodynamics, or QCD. In this framework, quarks carry a property called color charge, analogous to electric charge in electromagnetism. Just as electrons are attracted to protons because of opposite electric charges, quarks are bound together by the color force, mediated by particles called gluons. But the color force has a bizarre property that sets it apart from electromagnetism. While the electromagnetic force gets weaker as charged particles move apart, the color force gets stronger. Try to pull 2 quarks apart, and the energy stored in the gluon field between them increases. Eventually, there is enough energy to create a new quark-antiquark pair, and instead of freeing a quark, you just end up with more bound states. This explains why isolated quarks have never been observed. They are forever imprisoned inside composite particles called hadrons. Meanwhile, another piece of the puzzle was falling into place. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg developed a theory that unified electromagnetism with the weak nuclear force. In this electroweak theory, the photon, which carries the electromagnetic force, is related to the W and Z bosons, which carry the weak force. At very high energies, these forces merge into a single unified interaction. At lower energies, the symmetry is broken by the Higgs field, giving mass to the W and Z bosons while leaving the photon massless. The discovery of the W and Z bosons at CERN in 1983, with masses precisely matching the predictions of the electroweak theory, was a stunning confirmation. And with the discovery of the Higgs boson in 2012, the Standard Model was complete. Or was it? The Standard Model describes 17 fundamental particles organized into a beautiful mathematical structure. There are 6 quarks, up and down, charm and strange, top and bottom, arranged in 3 generations of increasing mass. There are 6 leptons, the electron, muon, and tau, along with their corresponding neutrinos. There are 4 gauge bosons, the photon, the W+, the W-, and the Z, which carry the electromagnetic and weak forces. There are 8 gluons that carry the strong force. And there is the Higgs boson, the excitation of the field that gives particles their mass. The mathematics of the Standard Model is based on a principle called gauge symmetry. This is a deep idea from quantum field theory that constrains the possible interactions between particles. The specific symmetry group of the Standard Model, written as SU3 times SU2 times U1, determines the structure of the strong, weak, and electromagnetic forces. Within this framework, physicists can calculate the outcomes of particle interactions with extraordinary precision. The magnetic moment of the electron, for example, has been calculated to more than 10 decimal places and matches experimental measurements to the same precision. This is one of the most accurate predictions in all of science, a testament to the power of the Standard Model. But for all its success, the Standard Model has deep flaws and unexplained features. Consider the masses of the particles. The Standard Model does not predict what these masses should be. The electron has a mass of about half a mega-electron volt. The top quark has a mass of about 173 giga-electron volts, roughly 340,000 times heavier. Why such a huge range? The Standard Model provides no explanation. The masses are simply parameters that must be measured experimentally and inserted into the theory by hand. The same is true for many other quantities. The strengths of the 3 forces, the mixing angles that govern how quarks and leptons interact, the amount of CP violation that explains certain asymmetries between matter and antimatter, all of these are free parameters of the Standard Model. The theory accommodates their values, but does not explain them. This might seem like a minor issue, an aesthetic complaint rather than a fundamental problem. But physicists have a strong intuition, born of centuries of experience, that a truly fundamental theory should have fewer free parameters, not more. A theory that requires dozens of unexplained numbers to be inserted by hand feels incomplete, like a puzzle with missing pieces. Then there are the outright failures of the Standard Model, the phenomena it simply cannot explain. Neutrino masses are one example. In the original Standard Model, neutrinos were assumed to be massless. But experiments beginning in the late 1990s showed that neutrinos oscillate, changing from one type to another as they travel. This can only happen if neutrinos have mass. The Standard Model can be extended to include neutrino masses, but doing so requires adding new particles and interactions that were not part of the original framework. Dark matter is another glaring omission. As we discussed earlier, astronomical observations tell us that most of the matter in the universe is invisible, interacting gravitationally, but not through the electromagnetic force. The Standard Model has no particle that fits this description. Whatever dark matter is, it lies outside the Standard Model. And then there is gravity. The Standard Model describes 3 of the 4 fundamental forces with exquisite precision, but it says nothing about gravity. Einstein's general relativity provides our best description of gravity, treating it as the curvature of space-time caused by mass and energy. But general relativity is a classical theory, not a quantum theory. Physicists have struggled for decades to develop a quantum theory of gravity that could be incorporated into the Standard Model framework, but so far without success. These are not minor gaps. These are fundamental limitations of the Standard Model that tell us something important. The Standard Model cannot be the final word on the nature of reality. There must be deeper theories, more comprehensive frameworks, waiting to be discovered. This is why physicists get so excited about anomalies. Every discrepancy between prediction and measurement, no matter how small, might be a clue pointing toward physics beyond the standard model. Every crack in the theoretical edifice might be a doorway to new understanding. The muon anomaly is particularly tantalizing because of what it might reveal about the quantum vacuum. Remember, the muon's anomalous magnetic moment arises from its interactions with virtual particles, the ghostly entities that flicker into and out of existence in the quantum foam. The standard model accounts for all the known virtual particles, electrons, quarks, W and Z bosons, gluons, the Higgs boson. But if there are additional particles that we have not yet discovered, they too would contribute to the muon anomaly. In other words, the muon is sensitive to particles we have never seen directly. It is a probe of the unknown, a detector of the invisible. A discrepancy in the muon's magnetic moment could be evidence for new particles too heavy or too weakly interacting to be produced in accelerators, but still able to leave their fingerprints on the muon's wobble. What kinds of new particles might be lurking in the quantum vacuum? One popular idea is supersymmetry. This is a theoretical framework that proposes a deep symmetry between the two main classes of particles in nature, fermions and bosons. In the standard model, fermions are the matter particles, quarks and leptons, while bosons are the force carriers, photons, gluons, W and Z bosons, and the Higgs. Supersymmetry suggests that every fermion has a boson partner, and vice versa. The electron would have a partner called the selectron. The photon would have a partner called the photino. The quarks would have squark partners. These superpartners have never been observed, which means they must be too heavy to be produced in current accelerators, if they exist at all. But even if superpartners are too heavy to be created directly, they could still influence the muon anomaly through virtual effects. Many supersymmetric models predict contributions to the muon's magnetic moment that could explain the observed discrepancy. If the muon anomaly is real, supersymmetry might be part of the explanation. Another possibility involves new gauge bosons. We know of 4 force carriers in the standard model: the photon, the gluons, and the W and Z bosons. But there could be additional force carriers that we have not yet discovered. A light, weakly interacting gauge boson, sometimes called a dark photon, could contribute to the muon anomaly while remaining hidden from direct detection. The idea of a dark photon is particularly intriguing because it might also help explain dark matter. If dark matter particles interact through a dark electromagnetic force mediated by dark photons, they would form a hidden sector of the universe, a shadow world running parallel to our own. The muon anomaly could be a window into this shadow world, a rare point of contact between the visible and invisible sectors. There are many other possibilities: leptoquarks, extra Higgs bosons, particles from extra dimensions, each with its own predictions for how it might affect the muon anomaly. The theoretical landscape is vast, and narrowing down the options will require more data, better calculations, and perhaps entirely new experimental techniques. For now, the muon anomaly remains one of the most intriguing hints of physics beyond the standard model. It is not conclusive. The theoretical uncertainties are too large. The disagreements between different calculation methods too significant. But it is tantalizing, a whisper from the quantum vacuum that something unexpected might be going on. And even if the muon anomaly eventually fades, even if improved calculations bring theory into agreement with experiment, the search will continue. Because the standard model cannot be complete. Somewhere, in some experiment, the first definitive crack will appear. And when it does, it will open a new chapter in our understanding of reality. Let us take a moment to appreciate just how remarkable this search is. We are talking about measuring the magnetic properties of a particle that lives for 2 millionths of a second. We are comparing this measurement to a calculation that involves summing over infinitely many virtual processes, taking into account every known particle and force. We are looking for discrepancies at the level of a few parts per million, searching for signals smaller than the uncertainty in many everyday measurements. This is precision science at its most extreme. It requires detectors calibrated to extraordinary accuracy, magnets controlled to a few parts per million, timing systems synchronized to the picosecond, temperature controls that maintain conditions to a fraction of a degree. It requires theoretical calculations that push the boundaries of mathematical technique, involving tens of thousands of Feynman diagrams, numerical integrations over vast multi-dimensional spaces, and careful assessments of every possible source of error. And it requires patience. The muon G-2 experiment at Fermilab collected data for 6 years. The CDF measurement of the W boson mass was based on data collected more than a decade before the result was announced. The calculations of the hadronic vacuum polarization have been refined over many years, with each improvement building on the work of previous generations of physicists. This is how science works at the frontier. Progress is slow, incremental, painstaking. There are no shortcuts, no magic insights that solve everything at once. Just careful, methodical work, repeated over and over, gradually narrowing the uncertainties, gradually sharpening the picture. And yet, despite the slow pace, the progress is real. We know incomparably more about the fundamental structure of matter than we did a century ago. We have a theory, the Standard Model, that describes a vast range of phenomena with incredible precision. We have experiments that can probe the quantum vacuum, measuring effects that were once thought forever beyond our reach. The muon anomaly, whatever its ultimate resolution, is part of this grand enterprise. It is a testament to human curiosity, to our determination to understand the universe, to our willingness to spend decades pursuing questions that might not have immediate practical applications. Because at some level, we pursue these questions simply because they are there. The universe exists. It has a structure. It obeys laws. And we want to know what those laws are. Not because the knowledge will help us build better smartphones or cure diseases, but because understanding reality is one of the most profound things a conscious being can do. There is a kind of spiritual dimension to this quest, even for those who do not think of themselves as spiritual. When we peer into the heart of an atom, when we study the dance of particles at nearly the speed of light, when we contemplate the vastness of cosmic time and space, we are participating in something larger than ourselves. We are connecting with the deepest truths about existence. The muon does not know that we are watching it. The quarks and gluons in the quantum vacuum do not care about our theories. The universe goes on its way regardless of whether we understand it or not. But we choose to understand. We choose to ask questions. We choose to seek answers. And in doing so, we become part of the story of the cosmos itself. Let this thought accompany you as you drift towards sleep. You are made of the same stuff as the muons in the storage ring at Fermilab. You are made of quarks and electrons and gluons and photons. You are made of the same fundamental particles whose properties physicists are measuring with such exquisite care. When we study the muon anomaly We are, in a sense, studying ourselves. We are trying to understand the building blocks from which we are constructed, the forces that hold us together, the laws that govern our existence, and we are doing this together as a species. The experiments involve thousands of scientists from dozens of countries. The theories draw on insights from mathematicians and physicists spanning centuries. The questions we are asking are the same questions that curious humans have asked since the dawn of consciousness. What is the world made of? Why does it behave the way it does? Is there more to reality than meets the eye? These questions drive us forward. They have led us from fire to electricity, from stone tools to spacecraft, from cave paintings to quantum computers. They have brought us to the brink of understanding the fundamental nature of reality itself. And now, at this moment in history, we stand on the edge of potential discovery. The muon anomaly, the Hubble tension, the search for dark matter, the quest for a quantum theory of gravity, all of these efforts are converging, all of them pushing the boundaries of the known. Something will break through, maybe not this year, maybe not this decade, but eventually the cracks in the standard model will widen and we will glimpse what lies beyond. We will discover new particles, new forces, new symmetries, new principles that unify the disparate pieces of our knowledge into a more complete picture. What will that picture look like? We cannot know in advance. The universe has surprised us before, and it will surprise us again. The theories of the future may be as different from the standard model as the standard model is from Newtonian physics, as Newtonian physics is from Aristotelian philosophy. But whatever we discover, it will be true. It will correspond to something real about the nature of existence. And that is a remarkable thing, that the universe is comprehensible, that the mathematics we invent turns out to describe the world we inhabit, that the patterns we detect in particle collisions connect to the patterns we see in galaxies billions of light years away. This is the cosmic mystery that underlies all the specific puzzles we have discussed. Why is there something rather than nothing? Why is that something orderly rather than chaotic? Why can minds like ours, products of evolution on a small planet, understand the laws that govern the entire universe? We do not know the answers to these questions. Perhaps we never will. But the fact that we can ask them, that we can make progress on related questions, that we can build machines like the Large Hadron Collider and theories like the Standard Model, this is its own kind of miracle. So let the muon anomaly be a symbol of all that we have achieved and all that remains to be discovered. It is a tiny crack in our understanding, perhaps, or perhaps it is nothing, a statistical fluke, a calculational error, a misunderstanding that will be resolved with more work. But even in that case, it represents the frontier of human knowledge, the edge of the known universe of ideas. And there is something beautiful about being at that edge. There is something thrilling about not knowing, about standing at the boundary between the understood and the mysterious. The questions we cannot yet answer are, in a sense, more precious than the answers we already have. They are invitations to discovery, doorways to the unknown, promises of wonders yet to come. As you rest tonight, carry this sense of wonder with you. The universe is vast and strange and full of secrets. We are small and brief and ignorant, but we are also curious and determined and capable of greatness. We have peered into the heart of matter. We have traced the history of the cosmos back to its first moments. We have asked questions that our ancestors could not even have imagined. And we have only begun. The muon is wobbling in its magnetic field, and we are watching, waiting, wondering what it might tell us. The W boson has been weighed and measured, and the results are still being debated. The light from distant supernovae is reaching our telescopes, carrying information about the expansion of the universe. The cosmic microwave background is whispering secrets about the early universe. All of this is happening right now as you listen to these words. The universe is revealing itself moment by moment, particle by particle, photon by photon. And we are here to witness it, to record it, to try to understand it. What a privilege that is. What an extraordinary gift, to live in an age when such wonders are being uncovered, to be part of a species that can ask such questions and make progress on answering them. Let gratitude fill you alongside the wonder. Gratitude for the scientists who dedicate their lives to this quest. Gratitude for the institutions that support them. Gratitude for the long chain of thinkers stretching back through history who built the foundations on which we stand. Gratitude for the universe itself, for being the kind of place where conscious beings can emerge and ask about their own origins. The crack in reality, if it exists, is an invitation. It is an invitation to look deeper, to think harder, to work more carefully. It is an invitation to discover something new about the cosmos, and, in doing so, about ourselves. And perhaps that is the deepest truth that physics has to teach us, that we are not separate from the universe we study, that the same laws that govern the wobble of a muon govern the beating of our hearts, that the same particles that were forged in the Big Bang compose our bodies and our brains. We are the universe trying to understand itself. We are matter contemplating matter. We are the cosmos becoming conscious of its own existence. And in that light, the search for cracks in the standard model is not just an abstract intellectual exercise. It is part of our self-understanding, our quest to know who and what we are. Every measurement of the muon anomaly, every calculation of the hadronic vacuum polarization, every observation of distant galaxies is a step on this journey of self-discovery. The journey is far from over. In fact, it may never end. There may always be more to discover, more questions to ask, more mysteries to explore. The universe may be infinitely deep, with layer upon layer of structure extending forever beyond our current understanding. But that is not a reason for despair. It is a reason for hope. It means that the wonder will never be exhausted, that there will always be new horizons to explore, that the adventure of discovery will continue as long as there are curious minds to pursue it. So rest easy tonight, knowing that the search continues. The muon is still wobbling. The calculations are still being refined. The experiments are still gathering data. And somewhere, in some laboratory or study, someone is having the insight that will unlock the next piece of the puzzle. You are part of this story. By learning about these mysteries, by caring about them, by wondering about them, you are participating in one of humanity's greatest endeavors. You are a fellow traveler on the cosmic journey, a companion in the quest for understanding. And the universe, with all its wonders and mysteries, is waiting to share its secrets with you. Let us continue a little further, exploring the philosophical implications of what we have discussed. Because the search for cracks in the standard model is not just about physics. It raises deep questions about the nature of knowledge, the limits of human understanding, and the relationship between mathematics and reality. One of the most remarkable aspects of modern physics is how much of it is driven by mathematics. The standard model is, at its heart, a mathematical structure, a set of equations that describe the behavior of particles and forces. Physicists do not simply observe nature and catalogue what they see. They construct mathematical models and compare the predictions of those models to experimental data. This approach has been spectacularly successful. The mathematical structures of quantum mechanics and quantum field theory have led to predictions of astonishing accuracy. The existence of particles like the W and Z bosons, the top quark, and the Higgs boson were all predicted mathematically before they were discovered experimentally. The mathematics seems to know things about the universe that we have not yet observed directly. This raises a profound question, one that philosophers have debated for centuries. Why does mathematics work so well in describing the physical world? The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. It is unreasonable in the sense that there is no obvious reason why the abstract structures invented by mathematicians, often for purely aesthetic or intellectual reasons, should turn out to correspond so precisely to the behavior of physical reality. One possibility is that mathematics is not invented, but discovered. According to this view, mathematical truths exist independently of human minds, in some kind of abstract realm, and we merely uncover them. The laws of physics are written in the language of mathematics, and by learning that language, we can read the book of nature. Another possibility is that mathematics is a product of the human mind, shaped by our evolution and our experience of the physical world. On this view, it is not surprising that mathematics describes the universe well, because mathematics evolved precisely as a tool for modeling our environment. The match between mathematics and physics is not unreasonable at all, but rather a natural consequence of how our brains developed. A third possibility is that we are suffering from a selection effect. Mathematics comes in many forms, and physicists have explored many mathematical structures in their quest to describe nature. It could be that we remember and celebrate the cases where mathematics fits the physical world beautifully, while forgetting the many cases where mathematical ideas led nowhere. The unreasonable effectiveness of mathematics might be partly an illusion created by our selective attention. Whatever the explanation, the relationship between mathematics and physics remains one of the deepest mysteries in our understanding of knowledge. When we search for cracks in the standard model, we are implicitly assuming that the mathematical framework of particle physics is at least approximately correct, that it captures something real about the structure of the universe. Any discrepancy we find is interpreted as a sign that the mathematical model needs to be extended or revised, but there is always the possibility that our entire approach is missing something fundamental. Perhaps the universe has aspects that cannot be captured in any mathematical framework, at least not one accessible to human minds. Perhaps there are limitations to what conscious beings embedded in physical reality can ever know about that reality. These are humbling thoughts. They remind us that for all our progress, we are still very much at the beginning of understanding. The standard model may be the most successful physical theory ever devised, but it is surely not the last word, and the framework that eventually replaces it may be as unimaginable to us today as quantum mechanics would have been to Newton. There is a famous saying attributed to Isaac Newton that if he had seen further than others, it was by standing on the shoulders of giants. Today's physicists stand on an enormous pile of shoulders, benefiting from the accumulated wisdom of countless thinkers over many centuries. But even so, the view from the top of that pile is limited. There is so much we do not see, so much we do not know. The muon anomaly, in this context, is both a challenge and an opportunity. It challenges us to refine our understanding, to push the boundaries of precision, to question our assumptions. It offers the opportunity to discover something genuinely new, to extend our knowledge into territory that previous generations could not explore. Whether the anomaly leads to a breakthrough or fades into the history of science as a false alarm, the process of investigating it is valuable. It sharpens our tools, deepens our understanding, and prepares us for whatever discoveries lie ahead. And this brings us to another philosophical point: the value of uncertainty. In science, as in life, we often crave certainty. We want to know the answers, to have solid ground beneath our feet, to feel confident that our understanding is correct. But uncertainty is not the enemy of knowledge. It is the engine of discovery. If we were certain about everything, there would be nothing left to learn. It is precisely because we do not know everything that we continue to search, to question, to experiment. The muon anomaly is a beautiful example of productive uncertainty. We do not know for sure whether it represents new physics or a miscalculation. That uncertainty drives enormous scientific effort. Thousands of researchers working on experiments and calculations around the world, all trying to resolve the question. And even if the anomaly turns out to be nothing, a mere statistical fluctuation, or a subtle error in the theory, the uncertainty will have been productive. The measurements will have become more precise. The calculations will have become more reliable. The experimental techniques will have been refined. All of this will be useful for whatever challenges come next. Uncertainty also keeps us humble. It reminds us that our current understanding, however impressive, is provisional. The theories we celebrate today may be the incorrect approximations that future generations shake their heads at. The questions we struggle with may turn out to have simple answers that we simply have not seen yet. This humility is essential for scientific progress. Scientists who are too confident in their theories may miss evidence that contradicts them. Scientists who are too attached to their ideas may resist new paradigms that would advance the field. The best scientists maintain a delicate balance, deeply immersed in current theory, but always open to the possibility that everything might change. The history of physics is filled with examples of confident theories being overturned. The Aristotelian worldview, with its perfect celestial spheres and its distinction between terrestrial and heavenly physics, lasted for nearly 2,000 years before being replaced. Newtonian mechanics seemed utterly secure for 2 centuries before Einstein showed that it was only an approximation to a deeper truth. And now the Standard Model, for all its successes, faces questions that may ultimately lead to its supersession. This is not a bug in the scientific process. It is a feature. Science advances by testing ideas against reality and revising them when they fail. The constant cycle of hypothesis, experiment, revision, and refinement is what allows science to correct its errors and converge toward truth. The muon anomaly is part of this cycle. It is a test of the Standard Model, a challenge to our current understanding. Whether the Standard Model passes or fails this test, science will advance. Either the model will be confirmed with even greater precision, or it will be extended to incorporate new physics. Both outcomes are victories for knowledge. Let us also consider the social dimension of this quest. Physics is often portrayed as the work of isolated geniuses, lone individuals who have flashes of insight that transform our understanding. And there is some truth to this image. Einstein working in his patent office, Newton hiding from the plague in the countryside, Dirac quietly scribbling equations. These are iconic figures whose contributions shaped the course of science. But modern physics, and particularly experimental particle physics, is profoundly collaborative. The experiments at CERN involve thousands of scientists from dozens of countries. The muon G-2 collaboration at Fermilab includes nearly 200 researchers from institutions around the world. The theoretical calculations that predict the muon anomaly draw on work by hundreds of physicists over many decades. This collaboration is not just a practical necessity imposed by the scale and complexity of modern experiments. It is a fundamental feature of how science works. Scientific knowledge is collective. It emerges from the interaction of many minds, the exchange of ideas, the critique and refinement of hypotheses. No single person, however brilliant, can advance a field as effectively as a community of researchers working together. The muon anomaly is a perfect illustration. The experimental measurement requires expertise in accelerator physics, detector technology, data analysis, and statistical methods. The theoretical calculation requires expertise in quantum field theory, lattice QCD, hadronic physics, and precision calculations. No individual could master all of these areas. Progress comes from specialists contributing their pieces to a larger puzzle. This collaborative nature of science is one of its great strengths. It provides redundancy, as multiple teams independently check each other's work. It provides diversity, as researchers with different backgrounds and perspectives contribute their insights. It provides continuity, as knowledge is passed from generation to generation, building cumulatively over time. And it provides a kind of global coherence. Scientists in different countries, speaking different languages, working in different institutions, all contribute to the same body of knowledge. The muon does not care whether it is studied in Illinois or Switzerland or Japan. The laws of physics are the same everywhere. And so the scientific community, despite all its internal disagreements and rivalries, forms a worldwide network dedicated to understanding reality. This is a hopeful image, especially in a world often divided by conflict and misunderstanding. Science shows that humans can work together across boundaries, that we can build shared knowledge, that we can make progress on questions that matter to everyone. The quest to understand the universe is a common human endeavor, one of the few truly global projects that transcends national and cultural differences. When you think about the muon anomaly, think also about this community of seekers, this global network of curious minds. Think about the graduate students running simulations late at night, the postdocs analyzing data streams, the senior scientists guiding research programs, the theorists filling blackboards with equations. They are all part of this story, all contributing to the search for understanding. And, in a sense, you are part of it too. By listening to this exploration, by caring about these questions, by wondering about the nature of reality, you are joining the community of the curious. You do not need a PhD in physics to participate in the wonder. The universe is open to everyone who cares to look. Let this thought comfort you as the night deepens. You are not alone in your curiosity. Billions of humans have looked up at the stars and wondered. Thousands of scientists are working right now, at this very moment, to answer questions about the cosmos. The muon is wobbling in its storage ring. The LHC is colliding protons. The telescopes are gathering light from distant galaxies. And all of this activity is directed toward understanding, toward truth, toward the simple desire to know what the universe is made of and how it works. This is, perhaps, the most human of all endeavors. The need to understand, to make sense of our surroundings, to find patterns in the chaos. This is woven into the fabric of our being. It is what drove our ancestors to track the seasons, to map the stars, to develop agriculture and writing and science. It is what drives us today to build particle accelerators and telescopes and supercomputers. The muon anomaly is just one small piece of this vast project, but it is a piece that captures something essential about what we are doing. We are measuring the magnetic wobble of a subatomic particle to 14 decimal places. We are comparing this measurement to calculations that involve summing over virtual particles flickering in and out of existence. We are looking for discrepancies that might point to forces and particles we have never seen. This is audacious. This is ambitious. This is, in the best sense of the word, insane. And yet, it is also deeply rational, the logical extension of our desire to understand pushed to its furthest limits. The universe rewards this audacity. It has given us the standard model, a description of matter and forces that works with breathtaking precision. It has given us general relativity, a theory of gravity that describes black holes and gravitational waves. It has given us quantum mechanics, a framework for understanding the atomic and subatomic worlds. And it may yet give us more. The muon anomaly, if it represents genuine new physics, could be the first crack in a dam that has held back a flood of discovery. It could lead us to supersymmetry, or to extra dimensions, or to a fifth force of nature, or to something we have not yet imagined. Or it might lead nowhere. The crack might close. The anomaly might fade. The standard model might survive this challenge, as it has survived so many others. Either way, we will have learned something. We will have pushed our understanding a little further, refined our techniques a little more, asked our questions a little more precisely, and we will be ready for whatever comes next. That is the spirit of science, not certainty, but inquiry, not dogma, but discovery, not the end of questions, but the endless pursuit of ever deeper ones. Let this spirit carry you into sleep. Let the questions swirl gently in your mind, unanswered, but alive. Let the wonder of the universe fill you with a peaceful curiosity. The muon is wobbling, the cosmos is expanding, the particles are dancing, and we are here, watching, wondering, waiting. What will we discover tomorrow? Only the universe knows, and it is not telling, at least not yet, but it will. Eventually it will. Sleep well, traveler. The journey continues. The night grows deeper now, and so does our exploration. We have traveled far together, from the underground tunnels of CERN to the philosophical heights of human understanding. We have met the muon, that heavy cousin of the electron, and watched it wobble in ways that might, just might, reveal cracks in our picture of reality. We have weighed the W boson and discovered that even the most careful measurements can lead to confusion. We have gazed outward to the expanding universe and found tensions in our measurements of its growth. But there is more. There is always more. The universe is inexhaustible in its wonders, and our journey tonight need not end yet. Let us venture further, into territories we have only glimpsed, into questions we have only hinted at. Let us talk about what happens when particles collide. Inside the Large Hadron Collider, protons are accelerated to energies that would have seemed like science fiction just a few decades ago. These tiny particles, each one a complex system of quarks and gluons, are guided by powerful magnets around the 27-kilometer ring, gaining energy with each lap until they are traveling at 99.999991% the speed of light. At 4 points around the ring, the two counter-rotating beams are brought together, and the protons collide. These collisions are not gentle meetings. They are violent events, concentrating enormous energy into an impossibly small space, recreating conditions that existed only in the first trillionth of a second after the Big Bang. When two protons collide at these energies, they do not simply bounce off each other. Instead, the quarks and gluons inside them interact, and the concentrated energy can transform into matter, creating new particles that did not exist before. This is the magic of Einstein's famous equation, E equals mc squared. Energy can become mass. Mass can become energy. The boundary between them is fluid. The detectors surrounding the collision points are designed to capture the debris from these explosions. They are among the most complex instruments ever built. Layers upon layers of sensors that can track charged particles, measure their momenta, identify their types, and record their energies. When a collision occurs, thousands of particles spray outward in all directions, and the detectors must make sense of this chaos, reconstructing what happened at the moment of impact. This reconstruction is never complete. Some particles, like neutrinos, pass through the detectors without leaving any trace. Others decay so quickly that they travel only a fraction of a millimeter before transforming into other particles. The physicists must infer the existence of these short-lived particles from the patterns of what they can observe, like detectives piecing together a crime from scattered clues. The Higgs boson was discovered in exactly this way. The Higgs particle itself lives for less than a billionth of a trillionth of a second before decaying, far too brief to be detected directly. But when it decays, it produces other particles, 2 photons, or 2 Z bosons, or 2 W bosons, or 2 bottom quarks, depending on the quantum dice roll of the moment. By looking for an excess of events with these signatures, by carefully reconstructing the masses of the decay products, physicists could identify the fingerprint of the Higgs, even though they never saw the Higgs itself. This kind of indirect detection is a recurring theme in particle physics. We rarely see the objects of our search directly. We see their effects, their decay products, their influence on other particles. We build our understanding not from direct observation, but from inference, from reconstruction, from careful analysis of patterns in vast amounts of data. The muon anomaly fits this pattern. The muon does not directly reveal the existence of new particles. Instead, it shows a tiny discrepancy in its magnetic properties, a discrepancy that could be caused by virtual particles flickering in the quantum vacuum. The new physics, if it exists, is hidden in the 15th decimal place of a measurement, accessible only through extraordinarily precise experiments and calculations. This is the reality of physics at the frontier. The easy discoveries have already been made. The particles and forces that interact strongly with ordinary matter have already been found. What remains is subtle, elusive, hiding at the edge of our detection capabilities. Finding it requires pushing technology and technique to their absolute limits. And yet, despite the difficulty, physicists press on. They build bigger accelerators. They develop more sensitive detectors. They refine their calculations to ever greater precision. They dedicate their careers to chasing signals that might not even exist. Why? What drives this relentless pursuit? Part of the answer is simply curiosity, that fundamental human drive to understand. But there is more to it than that. Physicists know that the standard model is incomplete. They know that dark matter exists, that neutrinos have mass, that gravity behaves in ways that quantum field theory cannot explain. They know that beneath the surface of our current understanding lies a deeper reality waiting to be uncovered. The muon anomaly is one possible entry point to this deeper reality. If there are new particles too heavy to be produced directly at the LHC, they might still leave their trace in precision measurements like the muon's magnetic moment. The muon becomes a probe of the inaccessible, a telescope pointed not at distant stars, but at the hidden structure of the quantum vacuum. This is a beautiful idea, that the tiniest deviations in the behavior of familiar particles might reveal the existence of entirely new physics. It connects the smallest scales we can measure to the largest questions we can ask. It links the wobble of a muon to the nature of dark matter, the origin of mass, the fate of the universe. Let us explore one of these connections more deeply. Let us think about what the muon anomaly might tell us about the mysterious dark matter that pervades the cosmos. Dark matter, as we have discussed, is one of the greatest puzzles in modern physics. We know it exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter they contain. Clusters of galaxies bend light from more distant objects more strongly than their visible mass can explain. This is a large-scale structure of the universe. The vast web of filaments and voids that galaxies trace out across hundreds of millions of light years matches simulations only when dark matter is included. But we do not know what dark matter is made of. The standard model has no particle that fits the bill. Dark matter cannot be ordinary baryonic matter, the protons and neutrons that make up stars and planets and people. It cannot be neutrinos, which are too light and move too fast to clump into the structures we observe. It must be something else, something beyond the standard model. Many theories have been proposed. One popular class of candidates are called weakly interacting massive particles, or WIMPs. These hypothetical particles would have masses somewhere between a few times and 1,000 times the mass of a proton. They would interact with ordinary matter through the weak nuclear force, or through forces even weaker than that. They would have been produced in the hot, dense, early universe, and a certain fraction would have survived to the present day, forming a diffuse halo around every galaxy. If WIMPs exist, they might occasionally scatter off atomic nuclei, depositing a tiny amount of energy that sensitive detectors could pick up. For decades, physicists have been building ever more sensitive experiments to search for these faint signals, deep underground in mines and tunnels where cosmic rays can interfere. So far, no definitive signal has been found. The limits on WIMP interactions have become extremely stringent, ruling out many of the simplest models. Another possibility is that dark matter consists of axions, hypothetical particles that were originally proposed to solve a different problem in particle physics, the strong CP problem. Axions would be extremely light, far lighter than electrons, and they would interact with ordinary matter only through incredibly feeble forces. Detecting them would require entirely different techniques than detecting WIMPs. Or perhaps dark matter is something stranger still. Perhaps it consists of primordial black holes, tiny collapsed objects left over from the Big Bang. Perhaps it is made of particles that interact through forces we have not yet discovered. Perhaps it is related to hidden dimensions of space, or to the quantum nature of gravity itself. The muon anomaly connects to this puzzle through supersymmetry. In many supersymmetric theories, the lightest superpartner particle is stable, meaning it cannot decay into lighter particles. This lightest superpartner would have been produced in the early universe and would still be around today. It would be invisible, interacting only weakly with ordinary matter. In other words, it would be a perfect dark matter candidate. If supersymmetry is the correct extension of the standard model, and if the muon anomaly is caused by virtual superpartners in the quantum vacuum, then the same new physics that explains the muon's wobble might also explain dark matter. The two puzzles, one from particle physics and one from astronomy, could have a common solution. This is why the muon anomaly generates such excitement. It is not just a curiosity about a subatomic particle. It is potentially a window into the nature of the invisible matter that dominates the universe. Solving the muon puzzle might help solve the dark matter puzzle. The tiny and the cosmic might be connected. Of course, this is just one possibility among many. Supersymmetry is not the only theory that could explain the muon anomaly. And even if the anomaly is real, it might point to physics that has nothing to do with dark matter. The universe is under no obligation to make our lives easy by connecting all its puzzles to the same solution. But the possibility is tantalizing, and it illustrates how different areas of physics are interconnected, how a measurement of a muon in Illinois can have implications for understanding galaxies billions of light years away. Let us follow another thread, another connection that links the muon to fundamental questions about the universe. In the first moments after the Big Bang, the universe was incredibly hot and dense. Particles and antiparticles were constantly being created and annihilated in a seething quantum soup. As the universe expanded and cooled, these creation and annihilation processes came into balance, and then fell out of balance, and eventually most of the matter and antimatter annihilated away, leaving behind a residue of ordinary matter. But here is the puzzle. If matter and antimatter are perfect mirrors of each other, if every process that creates matter also creates an equal amount of antimatter, then there should be no residue. The matter and antimatter should have annihilated completely, leaving behind nothing but radiation. No stars, no galaxies, no planets, no life. Clearly, this did not happen. We exist. The universe is filled with matter. Something must have caused a slight imbalance, a tiny preference for matter over antimatter, that allowed some matter to survive the great annihilation. This is called the matter-antimatter asymmetry, or more technically, baryogenesis. It is one of the great unsolved problems in physics. The Standard Model does include processes that violate the symmetry between matter and antimatter, a phenomenon called CP violation. But the amount of CP violation in the Standard Model is far too small to explain the observed asymmetry. Something beyond the Standard Model is needed. Where might this additional CP violation come from? There are many possibilities, and some of them connect to the muon anomaly. In certain theories of physics beyond the Standard Model, the same new particles that could explain the muon anomaly might also provide additional sources of CP violation. If these particles existed in the early universe, they could have tipped the balance in favor of matter, allowing some residue to survive and eventually form everything we see. This is another way that the muon connects to deep questions about the cosmos. Understanding why the muon wobbles differently than expected might help us understand why we exist at all. The physics that explains a precision measurement might be the same physics that explains the fundamental asymmetry that made the universe habitable. Again, this is speculative. We do not know for sure that the muon anomaly is real, and even if it is, we do not know that it connects to baryogenesis. But the possibility exists, and it motivates the intense scrutiny that physicists apply to every precision measurement. Let us turn to yet another connection, this one reaching into the realm of cosmology and the fate of the universe. We have mentioned that the universe is expanding, and that this expansion is accelerating. Something is driving galaxies apart at ever-increasing speeds, something that physicists call dark energy. Like dark matter, dark energy is a profound mystery. It makes up about 68% of the total energy content of the universe. yet we have almost no idea what it is. The simplest explanation for dark energy is the cosmological constant, a term that Einstein originally added to his equations of general relativity and later regretted. The cosmological constant represents a constant energy density of empty space, a sort of quantum pressure that pushes space to expand. If the cosmological constant is the explanation for dark energy, then empty space has a positive energy density. But when physicists try to calculate this energy density using quantum field theory, they get an answer that is catastrophically wrong. The calculated value is larger than the observed value by a factor of 10 to the 120th power. This is arguably the worst prediction in the history of physics. The discrepancy, known as the cosmological constant problem, suggests that we are missing something fundamental about the relationship between quantum mechanics and gravity. It is one of the strongest hints that our current theories are incomplete. Some physicists have proposed that the cosmological constant might be related to the physics of the standard model vacuum. The quantum vacuum is not truly empty. It seethes with virtual particles, the same virtual particles that contribute to the muon anomaly. The energy of all these virtual particles should, naively, contribute to the cosmological constant. If new physics exists that modifies the structure of the vacuum, it might help explain both the muon anomaly and the cosmological constant problem. This is a long shot, admittedly. The two phenomena seem very different, one involving a subatomic particle and the other involving the expansion of the entire universe. But physics has surprised us before with unexpected connections. The point is not that the muon anomaly will definitely solve the cosmological constant problem. The point is that these deep puzzles may be interconnected in ways we do not yet understand. Solving one might provide clues to solving others. The muon, for all its apparent insignificance, might be a key that unlocks doors to fundamental truths about the cosmos. This interconnection is one of the most beautiful aspects of physics. On the surface, particles and forces and cosmological phenomena seem disparate, unrelated, governed by different principles. But as our understanding deepens, we find unexpected connections, surprising relationships, underlying unity. Maxwell unified electricity and magnetism into electromagnetism. Einstein unified space and time into space-time, and energy and mass into a single entity. Glashow, Salam, and Weinberg unified electromagnetism and the weak force into the electroweak interaction. Physicists dream of further unification, a grand unified theory that would combine all the forces except gravity, and perhaps an ultimate theory of everything that would include gravity as well. The muon anomaly might be a signpost on the road to this greater unity. It might point toward supersymmetry, or toward extra dimensions, or toward some entirely new framework that we have not yet conceived. Following this signpost might lead us to answers about dark matter, about the matter-antimatter asymmetry, about the cosmological constant, about questions we have not yet thought to ask. Or it might lead nowhere. The anomaly might fade. The standard model might survive. The deeper unity might remain elusive for another generation. Either way, the search is worthwhile. The journey matters as much as the destination. The act of asking questions, of pushing measurements to their limits, of probing the boundaries of the known. This is valuable in itself, regardless of what we find. Let this thought bring you peace as the night deepens. Science is not about finding all the answers. It is about asking better questions. It is about refining our ignorance, learning what we do not know with increasing precision. Every experiment, every calculation, every theory tested and revised advances this project, even when the results are not what we hoped. The muon anomaly has already advanced our understanding, regardless of how it is ultimately resolved. It has pushed the experimental precision of magnetic moment measurements to unprecedented levels. It has spurred theorists to improve their calculations of the hadronic vacuum polarization. It has focused attention on the interplay between different approaches to quantum chromodynamics. It has motivated new experiments and new ideas. Even if the anomaly turns out to be a mirage, all of this progress will remain. The tools and techniques developed to investigate the muon will be used for other measurements, other searches, other discoveries. Science builds on itself, and nothing done carefully and honestly is ever wasted. So let the muon anomaly be a reminder of how science works, not as a series of triumphant discoveries, but as a patient, methodical process of refinement, not as a march towards certainty, but as an endless dance with uncertainty, not as the work of isolated geniuses, but as a collective endeavor spanning generations and continents. We are all part of this endeavor. Every curious mind, every wondering heart, every person who looks up at the stars and asks why, is participating in the great human project of understanding. You do not need to understand the mathematics of quantum field theory. You do not need to operate a particle accelerator. You just need to wonder. You just need to care. And as long as there are people who wonder and care, the search will continue. The muon will keep wobbling. The detectors will keep recording. The theorists will keep calculating. And maybe, someday, the cracks in reality will widen enough for us to glimpse what lies beyond. The night is deep now. The stars, if you could see them, would be wheeling slowly overhead, ancient light traveling across the void to reach your eyes. The same forces that govern the muon's wobble govern the fusion reactions in those stellar cores. The gravity that holds galaxies together, the expansion of space itself. You are embedded in this cosmos, made of its matter, shaped by its laws. When the muon wobbles, something deep within you resonates, even if you cannot consciously feel it. We are all connected, all part of the same vast web of particles and forces and fields. Let this connection comfort you. You are not alone in the universe. You are made of the universe. And the universe, through minds like yours, is beginning to understand itself. The crack in reality, if it exists, is not a threat. It is an invitation. It beckons us forward, deeper into the mystery, closer to the truth. It promises that there is more to discover, more to learn, more to wonder at. And that is perhaps the greatest gift the universe can give us. Not answers, but questions. Not certainty, but wonder. Not the end of the journey, but the promise that it will continue forever into realms we cannot yet imagine. Sleep well tonight, carried by this wonder. Dream of particles dancing in magnetic fields, of forces we have not yet named, of universes upon universes hidden in the quantum foam. Dream of the scientists working through the night, checking their calculations, analyzing their data, hoping to be the ones who finally crack the code. Dream of the future, when the puzzles we struggle with today will be solved, when new and deeper puzzles will take their place, when our descendants will look back on our efforts with the same mixture of gratitude and amusement that we feel toward our scientific ancestors. The muon is still wobbling. The universe is still expanding. The stars are still shining, and we are still wondering. What more could we ask for? Let the wondering carry you gently into sleep. Let the mysteries of the cosmos be your lullaby, Let the vastness of space and time wrap around you like a blanket, comforting in its immensity. Tomorrow, the search will continue. New data will be collected. New calculations will be performed. New ideas will be proposed and tested and refined. But for now, rest. You have traveled far tonight, through quarks and leptons, through forces and fields, through the history of physics and the philosophy of science. You have earned your rest. The universe will be here when you wake. The questions will still be waiting. The adventure will continue. And whatever cracks exist in reality, whatever secrets remain hidden, they will reveal themselves in time. Patience, curiosity, and wonder are all that is required. Sleep now, fellow traveler. The stars are watching over you. The muon is wobbling in its ring, and the universe, vast and ancient and strange, is smiling its cosmic smile, pleased that creatures made of its own matter have learned to ask such beautiful questions. Good night, but perhaps you are not quite ready for sleep. Perhaps there is still a spark of curiosity that keeps your mind from fully surrendering to the night. If so, let us linger a little longer in this space of wonder, exploring a few more facets of the extraordinary story we have been telling. We have spoken much about the muon and its anomalous magnetic moment. We have discussed the Standard Model and its limitations. We have touched on dark matter and dark energy, on baryogenesis and the cosmological constant. But there are other anomalies, other hints of physics beyond the Standard Model, that deserve at least a mention before we close this chapter. Consider the proton radius puzzle. For many years, physicists measured the size of the proton using two different methods. One method involves scattering electrons off protons and measuring how the electrons were deflected. The other method involves studying the energy levels of hydrogen atoms, where a single electron orbits a single proton. Both methods gave consistent results, yielding a proton radius of about 0.876 femtometers, less than a trillionth of a millimeter. Then, in 2010, a new measurement was performed using muonic hydrogen, an exotic atom where the electron has been replaced by a muon. Because the muon is 200 times heavier than the electron, it orbits much closer to the proton, making it much more sensitive to the proton size. The result was startling. The proton radius measured in muonic hydrogen was about 4% smaller than the value from ordinary hydrogen and electron scattering. 4% might not sound like much, but in the world of precision physics, it was enormous. The discrepancy was more than 5 sigma, well beyond the threshold for a statistical fluke. Either one of the measurements was wrong, or something deeply strange was happening. For years, the proton radius puzzle generated intense speculation. Was the muon interacting differently with the proton than the electron does? Was there some new force that affected muons but not electrons? Could this be another crack in the Standard Model? Eventually, the puzzle seems to have been resolved. New measurements of ordinary hydrogen using improved techniques have yielded proton radii closer to the muonic hydrogen value. The consensus now is that the original electron scattering and hydrogen spectroscopy measurements had subtle systematic errors that made the proton appear larger than it actually is. The puzzle, while not completely settled, appears to be a story of experimental challenges rather than new physics. But the episode illustrates how science works at the frontier. Anomalies appear, generating excitement and speculation. Careful work follows, testing hypotheses, improving measurements, searching for errors. Sometimes the anomaly reveals new physics. Sometimes it reveals the difficulty of precision measurement. Either way, we learn something valuable. The proton radius puzzle also highlights the special role of the muon in probing the structure of matter. Because muons are heavier than electrons, they can access regimes that electrons cannot. Muonic atoms, where muons replace electrons, provide exquisitely sensitive probes of nuclear structure. The same particle that might be revealing new physics through its anomalous magnetic moment is also a powerful tool for studying the familiar proton. Let us consider another class of anomalies that have attracted attention in recent years, the so-called B physics anomalies. These involve the decays of particles called B mesons, composite particles containing a bottom quark paired with a lighter quark. According to the Standard Model, B mesons should decay into different types of leptons, electrons, muons, and tau particles at predictable rates. The principle of lepton universality says that the electron, muon, and tau are fundamentally interchangeable, differing only in their masses. Any differences in decay rates should be entirely explained by these mass differences. For several years, experiments at the LHCb detector at CERN and at the Bell experiment in Japan reported hints that lepton universality might be violated. The ratio of certain B meson decays to muons compared to electrons seemed to differ from the Standard Model prediction. If true, this would be a clear sign of new physics, perhaps involving new particles that couple differently to different generations of leptons. The excitement was palpable. Theorists proposed models involving leptoquarks, hypothetical particles that could mediate interactions between quarks and leptons. They proposed new gauge bosons, new Higgs bosons, new symmetries. The B physics anomalies seemed like they might be the crack that would finally break the Standard Model. But as with the W boson mass anomaly, more data brought sobering news. In 2022, the LHCb collaboration reported new, more precise measurements of the key ratios. The results were consistent with lepton universality. The anomalies had faded. This does not mean that the search was wasted. The improved measurements provide more stringent tests of the Standard Model. The theoretical models developed to explain the anomalies are still valuable, as they explore the space of possible physics beyond the Standard Model. And the experimental techniques refined during this investigation will be useful for future measurements. Science is full of such episodes. Anomalies rise and fall. Excitement gives way to careful scrutiny. Some anomalies survive and lead to genuine discoveries. Others turn out to be statistical fluctuations, systematic errors, or incomplete theoretical predictions. The process is messy, unpredictable, and sometimes frustrating, but it is also self-correcting. In the long run, the truth emerges. The muon anomaly may follow the same pattern. It may persist, growing stronger as theory and experiment converge, eventually leading to the discovery of new physics. Or it may fade, like the B physics anomalies and the W boson mass discrepancy, resolving into a story about the difficulty of precision physics, rather than the discovery of new particles. We cannot know in advance which path history will take. All we can do is continue the work, continue the measurements, continue the calculations, and let the evidence guide us where it will. Let us also take a moment to appreciate the sheer scale of the effort involved in modern particle physics. The Large Hadron Collider is the largest and most complex machine ever built by humanity. It cost approximately $10 billion to construct and involves the collaboration of thousands of scientists from over 100 countries. The detectors that surround the collision points, ATLAS and CMS and LHCb and ALICE, are themselves marvels of engineering, containing millions of sensors, kilometers of cables, sophisticated cooling systems, and computing infrastructure that processes petabytes of data. The muon G-2 experiment at Fermilab, while smaller in scale, is no less impressive in its precision. The storage ring, originally built at Brookhaven and transported across the country, maintains a magnetic field uniform to a few parts per million across its entire 50-foot diameter. The detectors that track the decay products of muons must operate with timing accuracy measured in picoseconds. The analysis of the data involves sophisticated statistical techniques and careful accounting of every possible source of systematic error. These experiments represent decades of planning, construction, and operation. They are the products of countless hours of work by physicists, engineers, technicians, computer scientists, and support staff. Chorishchi. They embody the accumulated wisdom of generations of scientists who came before, who developed the theories, built the earlier experiments, and trained the researchers who work today. When we talk about the muon anomaly, we are talking about the fruits of this enormous collective effort. We are talking about measurements made possible by the dedication of thousands of people over many years. We are talking about questions that humanity as a whole is asking and trying to answer together. This is one of the most inspiring aspects of modern science. It demonstrates what humans can achieve when they work together toward a common goal. It shows that the quest for knowledge can transcend national boundaries, political differences, and cultural divides. Scientists from countries that are rivals in other arenas collaborate peacefully in the pursuit of understanding. The Large Hadron Collider is, in a sense, a monument to human cooperation. It exists because nations agreed to pool their resources, because scientists agreed to share their expertise, because the desire to understand the universe outweighed the forces that usually divide us. Whatever we discover at the LHC, the fact that we built it at all, is a kind of triumph. Let this thought bring you comfort as you drift toward sleep. In a world that often seems fractured and contentious, the scientific community offers a model of what collaboration can achieve. People of different backgrounds, different beliefs, different nationalities, coming together to ask the deepest questions about reality. This is humanity at its best, and the questions themselves matter regardless of the answers. The act of wondering, of investigating, of pushing the boundaries of knowledge, this is part of what makes us human. It connects us to the first humans who looked up at the night sky and wondered about the lights they saw. It will connect us to future generations who will ask questions we cannot yet imagine. The muon anomaly is part of this great chain of inquiry. It links the present to the past and the future, connecting us to Newton and Einstein and Dirac, and to the scientists who will come after us. We are participants in a conversation that spans millennia, a conversation about the nature of reality that is one of the noblest endeavors of our species. As you rest tonight, know that this conversation continues. Somewhere, a graduate student is running one more simulation, checking one more calculation. Somewhere, a detector is recording data, adding to the vast reservoir of information that scientists will analyze. Somewhere, a theorist is scribbling equations, searching for the insight that will make sense of it all. The universe is being investigated, moment by moment, around the clock, around the world. And every piece of this investigation, no matter how small, contributes to our collective understanding. You are part of this too. By learning about the muon anomaly, by caring about these questions, by wondering about the nature of reality, You are participating in the great human adventure of discovery. You do not need to be a professional scientist to be part of the quest. You just need to be curious. So carry this curiosity with you into sleep. Let it permeate your dreams. Dream of particles and forces, of detectors and accelerators, of mathematics and mystery. Dream of the universe in all its strange and beautiful complexity. And when you wake, the universe will still be here, waiting to share more of its secrets. The moon will still be wobbling. The experiments will still be running. The questions will still be beckoning. What will tomorrow bring? More data, perhaps, new measurements, refined calculations, maybe a breakthrough, or maybe just another step along the long road of understanding. We cannot know in advance. That is part of what makes science exciting. But we can know that the work will continue. As long as there are curious minds, as long as there are questions to ask, as long as the universe has secrets to reveal, the search will go on. The crack in reality, if it exists, will eventually be found. And when it is, it will open new vistas of understanding that we can scarcely imagine today. This is the promise of science. Not that we will find all the answers, but that we will never stop asking. Not that the journey will end, but that it will continue forever, into realms of wonder we have not yet dreamed of. Sleep well, fellow traveler. The universe is vast and ancient and full of mystery, but we are here, small and brief and curious, and we are learning. One muon at a time, one measurement at a time, one dream at a time. The stars are shining, the particles are dancing, the cosmos is unfolding, and we are watching, wondering, waiting to see what comes next. Rest now. The journey continues tomorrow. Good night, and thank you for joining us here at Cosmic Drift, where the mysteries of the universe are always waiting to be explored. Hati, if this journey has filled you with wonder, consider subscribing so you never miss our next exploration into the deep unknown. Sweet dreams, and we will see you among the stars. Before we truly part ways for the night, there is one more aspect of this story worth considering. We have journeyed through the physics, the history, the philosophy. We have explored particles and forces, experiments and theories, puzzles and possibilities. But let us take a final moment to reflect on what it all means, not just for science, but for us, for you, as you lie there in the gentle embrace of approaching sleep. The universe does not owe us comprehensibility. There is no cosmic law that says reality must be understandable to beings like us. Our brains evolved to help our ancestors survive on the African savanna, to track prey, avoid predators, navigate social hierarchies, and find mates. Nothing in that evolutionary history prepared us for understanding quantum mechanics or general relativity or the hadronic vacuum polarization. And yet, somehow, we can understand these things. The mathematics we invent turns out to describe the world. The experiments we devise yield results that make sense. The theories we construct have predictive power. This is remarkable. It is perhaps the most remarkable thing about our existence. The physicist Albert Einstein is often quoted as saying that the most incomprehensible thing about the universe is that it is comprehensible. Whether he actually said these exact words is debated by historians, but the sentiment captures something profound. The fact that minds like ours can grasp the deep structure of reality is not something we should take for granted. It is a gift or a mystery, or perhaps both. When we study the muon anomaly, when we measure the wobble of a subatomic particle to 14 decimal places and compare it to theoretical predictions, we are exercising this miraculous capacity for understanding. We are using brains that evolved for very different purposes to probe the most fundamental aspects of reality. We are doing something that, by any reasonable expectation, should be impossible. This is a source of wonder, not just the wonder at what we discover, but the wonder that we can discover anything at all. The universe is deep and we are small, yet we can reach into that depth. The cosmos is old and we are brief, yet we can understand something of its history. The fundamental forces operate at scales far beyond our direct experience, yet we can build machines that reveal their workings. Let this wonder be part of your rest tonight. You are a conscious being in an incomprehensibly vast universe, and you have the capacity to understand something of how that universe works. This is not a small thing. This is, in a sense, the entire point of having a mind capable of asking such questions. The muon does not know that it is wobbling. The quarks inside the proton do not know that they are quarks. The photons streaming from distant stars do not know that they carry information about the expansion of the universe. Only conscious beings like us can know these things. Only we can ask why things are the way they are and make progress toward answers. This makes us special in a certain sense. Not special in the sense of being at the center of the universe or being the purpose for which the cosmos was created. We have long since given up those conceits. But special in the sense that we are the part of the universe that has become aware of itself. We are matter that has organized itself into patterns capable of contemplating matter. When a physicist measures the muon anomaly, something astonishing is happening. The universe is studying itself. Atoms are investigating atoms. Particles are learning about particles. The boundary between the observer and the observed becomes blurry because both are made of the same fundamental stuff, governed by the same fundamental laws. This recursive quality of science, the fact that we are part of the reality we are trying to understand, is both humbling and ennobling. It humbles us because it reminds us that we are not outside observers looking in from some privileged vantage point. We are inside the system, products of the same forces we are trying to comprehend. Our understanding is necessarily partial, shaped by our position within the cosmos, but it also ennobles us because it shows that the universe has given rise to beings capable of self-reflection. The cosmos is not merely a collection of particles bouncing around according to blind laws. It is a process that has produced consciousness, meaning, and the search for truth. We are proof that the universe can know itself. The muon anomaly, in this light, is not just a technical puzzle for specialists. It is part of the grand human endeavor to understand our cosmic home. It connects us to the deepest questions about existence. What is the world made of? Why does it behave the way it does? Is there more to reality than we currently know? These questions have been asked by every human culture throughout history. They were asked by the ancient philosophers who first proposed that matter might be made of atoms. They were asked by the medieval scholars who studied the heavens and tried to discern the divine plan. They were asked by the modern scientists who developed quantum mechanics and discovered the expanding universe. And they are being asked today by physicists at CERN and Fermilab and laboratories around the world, using tools and techniques that previous generations could not have imagined. The questions are ancient. The methods are modern. But the underlying human drive, the desire to understand, remains the same. You are heir to this tradition. By listening to this exploration, by caring about these questions, you are continuing a conversation that stretches back to the dawn of human consciousness. You are participating in one of the defining activities of our species. This is something to take pride in, quietly, as you drift toward sleep. Not pride in any individual accomplishment, but pride in what humanity as a whole has achieved. We have come so far. We have learned so much, and we have so much more to learn. The muon anomaly is just one small piece of this vast puzzle, but every small piece matters. Every measurement, every calculation, every moment of wonder contributes to the great tapestry of human knowledge. The picture is far from complete. It may never be complete, but it grows richer and more detailed with each passing year. Imagine what future generations will know that we do not. Imagine the discoveries that will be made in the coming decades and centuries. Imagine the questions that will be asked that we cannot even formulate today. The adventure of science is just beginning. We stand at an early point in what may be an endless journey of discovery. This thought can be comforting as you rest. The work will continue after us. The questions will be pursued by minds we will never meet. The universe will keep revealing its secrets to whoever is patient and curious enough to look. We are part of a story much larger than ourselves. The muon anomaly is one chapter in that story. Other chapters have already been written. Many more remain to be written, and the story has no foreseeable end. Let this sense of continuity ease you into sleep. You are not alone in the universe, and you are not alone in wondering about it. Billions of humans share this planet with you, and some fraction of them share your curiosity about the fundamental nature of reality. Across the generations, countless souls have gazed at the same stars, pondered the same questions, felt the same awe. The cosmos connects us all. The particles that make up your body were forged in ancient stars. The forces that hold your atoms together are the same forces operating throughout the universe. The laws of physics that govern the moon govern you as well. You are made of the same stuff as the stars, the galaxies, the vast cosmic web stretching across billions of light years. This is not just a poetic sentiment. It is a physical fact. Every atom of carbon in your body was made by nuclear fusion in the core of a star that died billions of years ago. Every atom of iron in your blood was created in the violent explosion of a supernova. You are literally made of stardust. The universe has fashioned you out of itself, and now, through you, the universe wonders about itself. Through you, the cosmos contemplates its own nature. Through you, stardust asks where it came from and why it is here. What a privilege. What a mystery. What a gift. Sleep well tonight, stardust. Dream of the cosmos that made you. Dream of the particles that dance within you. Dream of the questions that define us as conscious beings. The moon is wobbling. The stars are shining. The universe is waiting. And tomorrow, the adventure continues. Good night, dear traveler, until we meet again among the mysteries of the cosmos. The night embraces you now. Let go of the day's concerns. Let the wonder of existence be your lullaby. The universe is vast, but you are not lost in it. You are part of it. You belong here. And so the story of the crack in reality comes to a gentle close, at least for tonight. The muon will keep wobbling in its storage ring. The theorists will keep refining their calculations. The experiments will keep gathering data. And somewhere, in the unknown depths of reality, the secrets we seek are waiting to be found. May your dreams be filled with cosmic wonder. May you wake refreshed and ready to face another day in this strange, beautiful universe. May the questions that drive science also drive you gently toward a life of curiosity and purpose. The stars are watching over you. The universe is smiling. Sleep now. Tomorrow, we wonder again. One final thought before the silence of sleep embraces you completely. There is a kind of magic in the fact that we can discuss these matters at all. The muon anomaly is expressed in numbers, precise measurements, and theoretical predictions that extend to many decimal places. These numbers represent something real about the universe. They encode information about how particles behave, how forces operate, how reality is structured at its most fundamental level. And yet, these numbers are also products of human minds. They are concepts we have invented to describe what we observe. The mathematics of quantum field theory, the statistical methods used to analyze experimental data, the computational techniques that enable lattice QCD calculations, all of these are human creations. We have built an elaborate conceptual framework that allows us to reach into the quantum realm and extract meaningful knowledge. This interplay between the objective reality of the universe and the subjective tools of human understanding is one of the deepest aspects of science. We are not merely passive observers recording what the cosmos presents to us. We are active participants, shaping our understanding through the concepts and methods we employ. The muon anomaly is out there in some sense independent of our awareness, but our comprehension of it is thoroughly shaped by the scientific framework we have constructed. This does not mean that science is purely subjective or that anything goes. The framework we use is constantly tested against reality, and it either works or it does not. The predictions either match the measurements or they fail. There is genuine constraint, genuine contact with something beyond our minds. But the knowledge we gain is always mediated by human concepts and categories. The muon does not care about our theories. It wobbles according to the laws of nature, whatever those laws might be. Our task is to discover those laws, to formulate them in ways we can understand, to test our formulations against observation. This is a humbling process because nature always has the final word. Sleep well, dear traveller. The universe awaits. Good night. Rest peacefully.